Now let's look at the joint probability density function in the continuous case, for continuous random variables. We've seen before that if x is a continuous random variable with PDF f of x, then the integral from negative infinity to infinity of f of x dx is 1. Similarly, if x and y are continuous random variables, they have a joint probability density function, or joint PDF or joint density function f of xy, such that the integral from negative infinity to infinity of f of xy dy dx is 1. This function f of xy is greater than or equal to 0, and we would use it to find the probability x and y take on particular values. For example, suppose x and y are continuous random variables with joint PDF f of xy equals 3xy squared over 4, where x is between 0 and 1 and y is between 0 and 2. So the region in which f is defined, in other words, the domain of f, is shown here. So notice here, x ranges from 0 to 1 and y ranges from 0 to 2. Find the probability that x and y are both x and y are less than a half. Well, if we wanted to find the probability that a continuous random variable x was less than a half, we'd calculate the integral from negative infinity to a half of f of x dx. Similarly, to find the probability that both x and y are less than a half, we'd calculate the integral from negative infinity to a half of f of xy dy dx. This is equal to the integral from 0 to a half f of xy dy dx, because f of xy equals 0 outside the interval x between 0 and 1 and y between 0 and 2. There's no need to go all the way down to negative infinity, because f of xy is just 0 when x and y are less than 0. If we want to find the probability that both x and y are less than a half, then this is the region we want to integrate over. Again, notice that x and y are both less than a half here. So the probability x and y are both less than a half is the integral from 0 to a half f of xy dy dx. That's the integral from 0 to a half 3xy squared over 4 dy dx. And when you evaluate this integral, when you evaluate this double integral, you end up with 1 over 256. Now, let's get back to that Society of Actuaries problem. A device runs until either of two components fails, at which point the device stops running. The joint density function of the lifetimes of the two components, both measured in hours, is f of xy equals x plus y over 8 for x between 0 and 2 and y between 0 and 2. Calculate the probability that the device fails during its first hour of observation, or first hour of operation, I should say. Okay, so the device fails when either component 1 fails or component 2 fails. We want to know the probability that component 1 fails during the first hour or component 2 fails during the first hour, or of course both. So we're looking at the probability x is less than or equal to 1 or y is less than or equal to 1. So in other words, we want to find the probability x is less than or equal to 1, y is less than or equal to 1. This is the domain of f shown on the left. Again, x ranges from 0 to 2, y ranges from 0 to 2. So this whole region here, that's what we're looking at. On the right is the region we want to integrate over. This is the probability that y is less than or equal to 1 or x is less than or equal to 1. So for example, the probability x is less than or equal to 1, that's all of this stuff over here. And the probability that y is less than or equal to 1, that's all of this stuff over here. And of course, this is the probability x and y are both less than 1. So thus the probability will be the integral over r of f of xy, where r is this region that you can see over here. The easiest way to express the integral over the region r is to break it into two regions. We have r1 and r2. Okay, so the integral of r1, that would be the integral of f of x. So the integral of f of xy over r, the double integral of f of xy over r1 plus the double integral of f of xy over r2. r1, notice r1 is going to be this region, and so our limits of integration, y goes from 0 to 2, and x goes from 0 to 1, and that gives you this whole region here. And then you would just integrate f of xy, that is x plus y over 8. As for this r2, to evaluate the integral over that region, we would let y go from 0 to 1, and then x go from 1 to 2, and we'll get this whole region, and thus that integral. Now the first integral, the integral from 0 to 1, 0 to 2, x plus y over 8 dy dx, when you evaluate that, you end up with 3/8. The second integral, the integral from 1 to 2, 0 to 1, x plus y over 8 dy dx, when you evaluate that, you end up with 1/4. So the total integral, the first integral plus the second integral, is 3/8 plus 1/4, which is 5/8, and so the answer is D.